So we want to recognize the different types of unsaturated hydrocarbons, one with double bonds and triple bonds, and alternating single and double bonds. These are named olefins, the alkenes. That's one with the double bonds. So we want to be able to name them if we're given a picture of one, and if we have a name of one, we'll be able to draw the picture. And we'll talk about some of the specific reactions that alkenes do. And then, like I said, we get into the really interesting stuff about isomers and what is really important in terms of biology is the concept of chirality. That's very important when we're talking about biological molecules. And so we'll define chirality and be able to see why it's so important in biology. I'll have several examples for you. So the first unsaturated hydrocarbon we're going to look at are the alkenes. And that's just simply a hydrocarbon with a carbon-carbon double bond. And we call that a functional group because that is a place that's basically different from your typical carbon-carbon single bonds and carbon-hydrogen single bonds. We'll talk a lot more about functional groups in the next chapter because we'll be dealing with functional groups that have oxygen in them, nitrogen in them, and sulfur in them. And they all have special chemistries for each one of those. Alkenes are called unsaturated because there are space for hydrogens that are now taken up by an additional bond between the carbons. That basically removes two hydrogens that could have been bonded to each one of those carbons, one each. Those are now gone and been replaced by an additional bond between the carbons. Now we have to remember that a double bond is shorter than a single bond. We haven't really gotten into the theoreticals about how double bonds are formed, but take it from me. For a double bond to form, the carbons have to be moved a little bit closer to each other because the electrons they share for a single bond are different than the ones they share for a double bond. And so the carbons have to move a little bit closer together in space. And that's also true for a triple bond. The carbons have to move even closer together in order to get all 6 of those electrons in the same space for them to be sharing. They're also stronger than a single bond. I mean, it takes more energy to break a double bond than it takes to break a single bond, but it's not additive. So the second bond in a double bond. So if I look at the energy of a single bond, when I add a second bond for the double, this second one is not as strong as the single bond. And that's why this extra bond is easier to break than a single carbon-carbon bond. And it explains why it's more reactive. And so we can break a single bond of the double, but breaking both of them is more difficult. And the double bond is not twice as strong as a single. It's about 1.8 times the strength, 1.6 to 1.8 times the strength. So some of the reactions that these double bonds engage in are pretty much all called addition reactions, where you have let me make that a little bit bigger, where you have your carbon-carbon double bond. One of them gets broken, and then that leaves electrons available to form a bond here and a bond there. And so we call that an addition reaction because we're adding things to where that double bond once was. And so some of the things that are going to be adding to it are hydrogen, water, and a lot of the times fluorine, chlorine, etc. So alkenes are more reactive than alkanes for that reason, because that second bond is not as strong. And those, as I mentioned, those electrons that are involved in making that bond are different than the ones forming the single bond. They're further away from the nucleus of the carbon, and it makes it easier to manipulate them. So you see a lot more reactions taking place with these electrons than these electrons in the single bond. Next unsaturated hydrocarbon we're going to deal with, and we're not going to deal with it all that much, are alkynes. And that is just basically any compound that has a triple bond in it. These are really reactive. They're shorter and stronger than the double bond. But again, it's not 3 times as strong as a single bond. It's actually about 2.4 times stronger than a single bond. But this bond and this bond, the non-single bonds, are not nearly as strong and much more amenable to reaction. So alkynes are even more reactive than alkenes. So they're super, super reactive. And so you don't really see them a lot in nature because they're so unstable. And one of the things that's made of alkynes that's unstable are these toxins that are found in the skin of the, anyone recognize this little guy? Do you know what that is?
Is that poison Parabi?
That's a poison tree frog, right? And the skin of poison tree frogs have these chemicals in them with extremely reactive triple bonds. And basically they're toxic for that very reason, because they just go around and just start reacting with all sorts of molecules in anybody who tries to bite them. So they have these bright colors to basically tell the potential prey that, yeah, you don't want any part of this. And then if they still don't get the message, the toxin will certainly get the message for them. So we don't see a lot of alkynes in nature, so we're not really going to talk about them much, but just be aware that basically any carbon compound with triple bonds in it is an alkyne. And then a really interesting group of unsaturated hydrocarbons are called the aromatics. We'll be talking a lot about them because they're also very important biologically. Now, unlike alkenes and alkynes, these aromatic molecules are unusually stable. They're really stable. You have to really force them to undergo reactions. And it's because their bonding is different than simple double bonds and triple bonds. What you have is generally a 6-ring compound, 6-carbon ring, and it's generally represented with alternating double and single bonds. But it doesn't actually have alternating double and single bonds, because if we look at the distance between these carbons, we would predict that if they were alternating double and single bonds, that the single bonds would be longer and the double bonds would be slightly shorter. But every single bond in this 6-carbon ring is exactly the same length. And it's just in between. It's shorter than a single bond, but it's longer than a double bond. And so what we say that it actually has a bond order, and that is just basically how bonded are these carbons, of 1.5, meaning they're not singly bonded, they're not doubly bonded either. They're bonded sort of in between, in the middle. And the reason for that is that these 6 electrons that would normally be in the double bonds are free to associate, and they go basically around and around and around the ring. They're free to move along the extra 6 carbons, and they're therefore less likely to react with other molecules, because in order to react with something, you need to have those electrons in one place and then manipulate them. These are in constant motion around the ring. And so it's hard to, basically some other compound to come in, grab them, manipulate them, and do a reaction. And so these cyclic compounds are really, really stable. So there's 2 ways to draw them. We can draw them like this. Oops. We can draw them like the way I just showed you, with 1, 2, 3, 4, 5, 6. So you draw them like that. You can put the double bond in the other place, or what a lot of organic chemists do is just draw a circle in the middle, because what that indicates is that all these bonds are equivalent, that you don't really have a double bond here and a single bond here, because you don't. You have something that looks more like this, where all the carbons are in exactly the same situation. So either way you want to draw them is fine. One thing that these aromatic rings can do is sort of fuse together and form these much larger rings called polycyclic, because more than one cyclic, aromatic hydrocarbons, or PAHs. These are really, really dangerous. Some of them, not all of them, but some of them. Some of them have been shown to be carcinogenic. And so these things can get stuck in between the rings of DNA. And we'll talk about DNA a little bit later as well. There are aromatic rings in DNA. And so these rings, one of the things about benzene that I forgot to mention is that it's completely flat. This is a planar molecule. So it is flat, flat, flat. And so it can slip into very small spaces, and particularly between other rings. And since DNA has rings, these will fit into rings. Benzene does too. Benzene's also a carcinogen. So it fits between the rings, and it screws up the replication of your DNA. And so it introduces a lot of errors, which lead to potential mutations and potentially cancer. So we don't want to have those around for the most part. So here are some of the compounds that we've been talking about. What about number 1? What family of hydrocarbon is A here?
Alkene.
It's an alkene, right? Because it has a double bond. So we call that, oh man, alkene. B, what about this one? That's that smell. If anyone's had mothballs, you get that weird kind of smell off them. That's why aromatic compounds, well, I just told you it's aromatic. That's why aromatic compounds are called that. They have really strong smells to them. And naphthalene is basically 2 fused benzene rings. And that strong smell keeps the moths from like eating all your sweaters or whatever else. What about this one? What family of hydrocarbon is that?
Alkene.
Alkane, that's right. It's highly substituted, but it's still an alkane because those are all single bonds. Okay, great job. So let's talk about naming these things. So our good old Union of Pure and Applied Chemistry has specific names and naming regimens for each one of these things. So One thing that's different about alkenes and alkanes is that we have to include the double bond in the parent chain. You remember we were dealing with alkanes. If we had a whole bunch of substitutions off it, we would just find whatever the longest continuous series of carbons was, and that would be it. It would be octane or heptane or whatever it was. But when there's a double bond, we have to include that in the parent chain, even if it isn't the longest. So there may be a chain of just 4 carbons that have a double bond in it, and then it's a substituent that has 7 carbons coming off of that. But because we have a double bond, that becomes the parent chain, and then that longer chain that has all single bonds becomes the substituent. So that's a different rule. We just end it in "ene" rather than "ane," so that's fairly straightforward. And we need to say where the double bond is. If there's more than 4 carbons, we have to say where the double bond is. And we always give the number to the first of the 2 doubly bonded carbons. And we also try and give it the lowest number we possibly can. So if it's right at the end, we call it 1. Second one in, 2, third one in, 3. And then if you need to flip it around, if it's the last carbon, well, then that becomes 1. And we go in the opposite direction. And then the rules for naming substituents are just the same as alkanes, and their positions indicated by a number. But we do give priority to giving the lowest number to the double bond. So if there's a methyl group, for instance, at position 2, and a double bond at position 3, we try and make the position of the double bond the smallest number we possibly can, and then name everything else from there. And we'll give some examples. In fact, we'll give an example right now. So how would we name this particular compound? And I've included the lists so we can remember. I still have trouble with propane and butane. I'm constantly mixing those up. So what is the longest continuous chain of carbons that contains a double bond?
Is that butane? Oh, sorry, 4.
No, longer than that.
Oh, my bad. 1, 2.
7.
Yes, let's write them off. So 1, 2, 3, 4, 5, 6, 7. Correct. So, and there's a substitution at what position?
2.
Nope.
Oh,
For the
I was
double
reading the
bond.
double. 5.
5. Right. So what are we going to call this thing? So remember, we call the substitutions first, and then we give the root name. So what are we going to call it?
Is it 5-methyl?
5-methyl.
Heptene?
Heptene is correct, but we still have to say where the double bond is.
2-heptene.
2-heptene, that's right.
Oh, so the substituents go first.
Heptene, yeah.
And then after that, you list
So
the
the 2 tells us where the double bond is. And we always give it to the first carbon that's double bonded, not the second one. So if it was 1-heptene, the double bond would start with this first carbon. Excellent.
So you first list the substituents, whatever substituents they are, and then the position. And
Yeah.
then after that, you start listing whether it's double or triple bond, and then the location where the double or triple bond begins.
Mhm.
Okay.
That's right. Yeah, it's the exact same rules we used before with alkanes. The only difference being we also have to say where the double bond is. We didn't have to do that with alkanes because there weren't any. We would just say it's 5-methylheptene. That'd be it. But there's a double bond there now. And so we have to indicate where it is, because those would be different molecules. They would be isomers of each other, but they would be different molecules and have different reactivity. So let's look at some of the aromatics. So any hydrocarbon that has this sort of ring structure to it, we call it aromatic. So this is called benzene, and that is basically the foundation of all the aromatic hydrocarbons. And we'll find out later that benzene with substituents basically takes on different names. And I'll tell you what they are. So they are hexagonal, and as I mentioned, they are planar. They are super, super flat. And all the carbons are equivalent, and the molecule is super, super stable. So you can draw it like that, or again, draw it like this. Either way, either one is correct. This is what the Lewis structure would look like. But of course, this is one of the instances where the Lewis structure is not correct, because it doesn't actually have alternating double and single bonds. It doesn't. So the Lewis structure sort of falls down with this particular molecule. We also have special names for where the positions of the substituents are. So when the two substituents are right next to each other, so they're on adjacent carbons, we call that ortho, right next to each other. When there's a carbon in between, we say that's like meta, man. That's like so meta. So there's one in between them. And when they're on opposite sides of the benzene ring, we say that they're in para position to each other. So all of these molecules are dichlorobenzene, but they're different. This one is 1, 2, and whatever the first substituent is, we always give it the position 1. So it doesn't really matter. If that's 1, then this is 2. If that's 1, then this is 2. And the same with 1, 3 and 1, 4. Basically, it just tells you how far apart they are on the ring. So we can call them 1, 2, 1, 3, and 1, 4 dichlorobenzene. We could also call them ortho-dichlorobenzene, meta-dichlorobenzene, and para-dichlorobenzene. And organic chemists use this a lot because it's really important in the chemistry. Like when synthetic chemists are like making drugs or something, when they want a particular reaction to take place, it's really important where the substituents are. If they're next to each other, they have more reactivity than when they're 1 away or 2 away. So they have to make sure that they're getting the right dichlorobenzene to do their next reaction, because one of them will react the way they want and the other 2 won't. So they've sort of developed this shorthand, ortho, meta, and para, to make that abundantly clear. Let's look at some of the reactions that alkenes do. So they're all basically just addition reactions, as I mentioned. What does that mean? It basically means that this second bond of the double bond is broken. Remember, with these reactions, not all of the carbon-carbon bonds are broken, just one. So we still are, once an addition reaction takes place, we still have a single bond there. It's just that we'd added something to where that second bond was before. So we break that bond, now have free electrons that are now available to bond with something else. And this first reaction is fairly straightforward, hydrogenation. And this is the reaction that takes place when you have either a single double bond, or you'd have multiple double bonds in the presence of hydrogen and generally a catalyst such as nickel, platinum, or palladium. Those are used because on the surface of those metals, they can actually absorb a tremendous amount of hydrogen gas. And when you want a reaction to move forward, one of the ways you can do that, you remember we sort of learned this in the last chapter, is increase the concentration of one of the reactants, right? That basically pushes the reaction forward. Well, on the surface of the metal, the concentration of hydrogen gas is huge. It's much, much higher than it would be just floating around. Because remember, in a tank of gas, most of the space is empty. There's nothing there. And so having a reaction takes place with a gas when there's like nothing there is a lot more difficult than if you have an extremely high concentration of gas on the surface. And so that pushes the reaction forward. And so this top bond gets broken, and taking its place are the two atoms of a hydrogen molecule. So we call that hydrogenation. And this is the reaction that margarine makers use. They take vegetable oil, which has a lot of double bonds, and they'll put it in the presence of, platinum, palladium, or some other metal, heat it, add hydrogen, and those double bonds get broken and replaced with hydrogen, and you get saturated fats, which now become solid at room temperature. And that's basically how margarine gets made from vegetable oil. So it's a little bit different from butter, which is actually obviously made from cream and animal fats.
So this is just like to break the double bond to make it into single bonds.
You leave it, yes, you leave one of the carbon single bonds behind, but you break that one bond, which now releases electrons that now can react with something else. And so that first reaction, hydrogenation, they just react with a hydrogen molecule. One hydrogen goes to one place, one hydrogen goes to the other. This one is slightly different. This one has we're going to talk about some more because this has some interesting chemistry going on. This is called hydration. And you can probably imagine what that means, right? Hydration probably has something to do with water, right? Yes, it has something to do with water. In fact, water gets added to the molecule. But when it does, this basically splits, and we get hydrogen being added to one of the carbons and a hydroxyl group added to the other. So here's the double bond. It gets broken, and then, so let's look at carbon 1 and carbon 2. Carbon 1 gets the hydrogen, and carbon 2 gets the hydroxyl. And so we go from ethylene to ethanol. So we've created an alcohol. Okay. And this usually requires catalysts, usually something like sulfuric acid. Sulfuric acid, a strong acid, basically is like pulling a bowstring. It pulls the string of that double bond and makes it a lot more reactive. So the water comes along, and then with this really, really drawn bowstring and high energy, just slips in there and boom, replaces it across this bond. We'll talk more about aldehydes and ketones in the next chapter. Those are also oxygen containing groups. But for now, we're going to be talking about hydration. Now, why this is an interesting, somebody, question.
Oh, no, I just wanting to make sure I understood that. So for hydrogenation, basically the bonds are broken. So it has
One
space.
bond is broken.
Yeah, one of the double bond
Yep.
is broken. So it leaves space so it can have another kind of reaction.
Mhm.
Whereas for this one, it's just kind of stretched and split apart.
Yeah, I mean, the same thing. I mean, you need, these things happen much faster when you push them. And so the hydrogenation, basically we push that reaction just by vastly increasing the local concentration of hydrogen. So we have like basically an infinite concentration of hydrogen that pushes that reaction forward. With this one, the sulfuric acid basically makes that double bond even more reactive. It changes the distribution of electrons in that double bond, which then allows water to go in there and take and react with it. It's because water has, and everyone will remember this, these two lone pairs of electrons. And so near those two lone pairs of electrons, if what the acid does is make these carbons slightly more positive than they were before. And so oxygen is now, as we know, has a slightly negative charge. And then that goes in there, and then the reaction takes place. We won't really go into the reaction mechanisms. It's a little more advanced than this class. But if you were to take another organic chemistry class, I'm sure you're all dying to do that, we would get into SN1 and SN2 reactions and nucleophiles and all that good stuff, but we're not going to do that. So right now we're just going to focus on the group coming in basically has a bond that gets broken too. And so we break that bond, and one of the reactants goes there and the other one goes to the second carbon. Same with the water. This bond gets broken between the hydrogen and the oxygen. One of them goes to one carbon and the other part goes to the other carbon. What's interesting is that we can predict where the hydroxyl group is going to go and where the hydrogen is going to go. They always go to the same place. So, which is kind of weird, but let's have a look. So here we've got a carbon-carbon double bond, but you see it's not symmetrical. Carbon 1 has a methyl group attached to it. Carbon 2 just has two hydrogens. So they're not equivalent, they're not the same. So we throw our acid into the reaction, that breaks, and the hydroxyl group goes to carbon 1 and the hydrogen goes to carbon 2. And it's not sometimes, or 50% of the time, it's all the time. The hydroxyl group always goes to the carbon that has more carbon groups attached. So carbon 1 has a carbon group attached. Carbon 2 does not. So CH2 becomes CH3. And that is always the case. And that is weird because we normally think of reactions like, 50% of the time the hydroxyl will go to that side, and 50% of the time the hydroxyl will go to that side. But that doesn't happen. That will happen if you have a catalyzed reaction, or if you have a reaction with an enzyme catalyst, because an enzyme has a very specific shape. But this just happens in solution by itself. And the first person to notice this was a Russian named Vladimir Markovnikov. And he's given credit for noticing this, and he actually figured out why as well. And so we call this Markovnikov's rule. And so we'll be using this a lot to be able to predict which carbon is going to get the hydroxyl group and become an alcohol and which carbon won't. So one easy way to remember is wherever there are hydrogens, they're going to get more hydrogens. So we have CH2 here. Well, it's going to be CH3, and that's always the case. If the other carbon doesn't have any carbons attached to it, if it's just all hydrogens too, then it's just, it's completely random. But if this has if this has a methyl group or an ethyl group or a propyl group or two methyl groups attached to it, that is where the hydroxyl group, the OH, that's where it's going to go. So any questions about good old Markovnikov? All right, let's see if you remember them. Let's have a look at some of these. Now, these are hydrogenation reactions. So we don't really have to worry about Markovnikov with this. So what is this going to look like after hydrogenation?
It's going to have a single bond.
Let's say carbon 1, carbon 2. So we're going to break one of the bonds. And then what gets put at carbon 1?
A hydrogen for each carbon.
Right. So you just put a hydrogen at each place. Now, what about B? Now, the cool thing.
Sorry. So,
yes.
So the way that you draw that structure is just like that, like where the hydrogen, there's two hydrogens attached to each
Yeah. So
carbon.
one hydrogen atom goes to carbon 1, and one hydrogen atom goes to carbon 2.
Oh, I see it. Sorry, it's just the diagonal is throwing me off.
Yeah. So each carbon has 4 bonds. So before, carbon 1 and carbon 2 had a double with each other. That's 2, and then a bond with another hydrogen, and then a bond with an propyl group. So now we just added the hydrogen to each one and get rid of the double. Now the fun thing about these products, when you're looking at the skeletal structure, drawing the product for a skeletal structure hydrogenation reaction is really easy. It's super, super easy, because what do we have to do in order to make this look like it's missing a double bond and it's hydrogens instead?
You just add another diagonal line.
Actually, we don't add anything. Because remember, diagonal lines in a skeletal structure indicate a carbon-carbon bond. So if I make a line, that indicates there's a carbon on one side and a carbon on the other. So I'm not adding any more carbons, so I can't draw any more lines.
So just remove the double bond.
Exactly. I just get rid of the double bond and then I'm done. Because the assumption, remember, when you're dealing with these skeletal structures, is that I only am drawing carbon-carbon and carbon carbon-carbon bonds and carbon bonded to anything other than hydrogen. Everything else I would include. If it's bonded to oxygen, I include it, or nitrogen, I include it, or sulfur, I include it. But if it's just bonded to hydrogen, I leave it out. So really, all you need to do is just remove that double bond and you're done. So for instance, here, what's this called?
Cyclopentine.
Cyclopentene, exactly. So it's got 5, so pentane, but it's got a double bond, so pentene. And we don't have to say, why don't we have to say like 1 cyclopentene? Why is there no number?
Because it's on the first one.
Yeah, because we just assume that wherever the double bond is, that's the number 1. And it doesn't really matter because they're all the same. So 1, 2, 3, 4, 5 cyclopentene are all the same compound. They're all exactly alike. So all we would have to do, what would be the product of cyclopentene undergoing hydrogenation?
Just erase the line.
Right, and then what do we get? What's that?
Cyclopentane.
Cyclopentane, exactly. So yeah, so believe me, if I give this to you on a test, it'd be like the easiest question you'll ever have to do. Just basically draw exactly the same structure without the double bond and you get it right. So
That's on our exam, right? I know
Yes.
you put up the second
yes, your
exam.
final
right?
final will just be 50 of those worth 2 points each. Yeah, of course. So let's talk about isomers. Now we're getting into some fun stuff in biology. So isomers, there's a couple of different kinds of isomer. One that we're probably familiar with already, and one we're probably not. So an isomer is just a compound having the same formula, but a different structure to them. They're put together differently. So butane, we know, has 4 carbons. I sometimes remember that, and no double bonds. So that's one way of drawing it. That's another way of drawing it. And those are different. Why? Because this one has 4 carbons in a row, and this one only has 3. So those are different molecules, but they have exactly the same formula. They're both C4H10. So we would call those structural isomers because the structure of them is different. So that's one's fairly straightforward. So molecular formula is the same, but the structural formula in the chemical properties are different. So that's one we probably knew before, but there's also different types. So this just gives you another example. I don't know why I included this. It's a different example, same thing. So this just shows you that the shapes of them are different. So there's our friend, again, all in a line. So remember, when it's all in a line, we call it N. And then when it's sort of broken up like that, if there's 3 of them, we call it iso. So those 2 are structural isomers, but they're not the only kind of isomers. You could also have a conformational isomer. Now these would be a different shape, but the connectivity of the carbons is the same. So basically, there's 2 ways we can draw that molecule. Remember, when we're doing the skeletal structure, we can go 1, 2, 3, 4. 1, 2, 3. Oops, put 1 too many in there. We can just go 1, 1, 2, 3, 4, or 1, 2, 3, 4. Now, in each, they're both exactly the same. They both have 4 carbons, and each carbon is in a row. They're all connected to each other in the same way, but they're a different shape. So those aren't different compounds, but slightly different arrangements in space. So these are just shape differences. And so shape or conformation means conformational isomer, or sometimes called conformers. So those are exactly the same molecule, but bent in different ways.
That second one, it looks like 3. At least
Yeah.
that's how I would read it.
Right, but it isn't, right? Because 1, 2, 3, and that is 4 in a row.
I meant by the skeletal structure, it looks like just 3.
Oh yeah, but remember, each line is 2 carbons. I get that wrong all the time too. So
Is that because
1,
of the
2,
location?
3, 4. Exactly.
Because it's at the
Exactly.
Oh, I see. Okay.
Because if you were to bend it, it's still all in a row. It's just now it's
Mhm.
kind of bent upwards. So
Exactly. Excellent point. That's exactly right. Because single bonds can rotate. And the way I explained it, if you watch and I know you're all watching my weekend videos, if you take a single bond, just think of it as like this, you have your two fingers and you can rotate, you can keep them together and rotate them around and still keep your fingers connected to each other. Now, do it with two fingers. You can't rotate them because if you want to rotate them around, you have to break one in order to rotate them. So a double bond, basically you're stuck in space. So if I have, notice one of my thumbs is up and the other one is down, and I can't move them. I can't rotate a double bond, but with single bonds, you can freely rotate and come up with all kinds of different shapes. And that leads us to a number of interesting types of isomers we'll get to in a minute. So, A, are those two the same compound or are they isomers? And that should say CH3 here. That's a typo.
So would that one be the conformational isomer?
Well, look a little more closely though.
I think it's two different compounds.
Yeah,
Yeah, they
those are
look
two
different.
different compounds, actually.
Oh, there's one more extra of the,
Mhm.
I see it. I
Yeah,
just-
and they're not, yeah, those two aren't even isomers because this one is a C4 and this one is a C5. What about the second one, B?
I think they're the same compound, but different arrangement. Right.
Okay, so if it's a different arrangement, then is it exactly the same thing or are they isomers of each other?
Oh, I mean isomers.
Those are isomers, right? Because in this one is 1, 2, 3, 4, 5, and they're all in a row. So we would say that is N-pentane because they're all in a line. And this one has 1, 2, 3, 4 in a line with a methyl group coming off of number 2. So that is 2-methyl butane. They have the same formula, but a different structure. So those are structural isomers.
Sorry, why did you put the N before pentane?
N just means that they're all in a line.
Oh,
Yeah, so N-pentane is just 5 carbons in a row. N-hexane, 6 carbons in a row. It just means you don't have any branches.
oh, okay. So you don't
Yes.
have like the methyl or the ethyl or any
Right, you don't
of
have
those?
any of that. It's just one long, just like a snake. Think of this
Oh,
like
okay.
snake pentane, just long and without any, legs or anything.
Okay.
All right, let's look at these. So here, these two. Structural isomer, conformational isomer, or completely different molecules. So that has 1, 2, 3, 4, 5 carbons. And so does this, 1, 2, 3, 4, 5. So we know they have the same formula. Are they structural isomers or conformational isomers?
That one's conformational.
That one's conformational, right? Because
Those in a
this
row and big
one,
box.
they're both all in a row, but this one is a different shape. But in fact, we don't know what shape that is, presumably just straight. We don't really know. Now, let's look at the second one. I've got this molecule and this molecule. This one has 1, 2, 3, 4, 5, 6 carbons, and this one has 6 carbons as well. So they would have the same formula. There's no double bonds. They're all single bonds. So they would have this, should have the same number of carbons.
Would this one be structural?
Yeah, that one's structural. They're different. Yeah, this one is cyclohexane, and this one is methyl cyclopentane. So those are different molecules that have the same formula.
So structural just means structurally they're different, I guess, and then conformational, is it just The
Different
way
shape,
okay.
just a different shape, just bent in a different way. Yep. And basically, another good way to look at it is if you were to name them, would they have different names? And so if we look at A, I would just call that 1, 2, 3, 4, 5 pentane, and B, this one 1, 2, 3, 4, that's pentane. So they both have the same name, but these two have different names. So that basically indicates they're put together differently. They're not just different shapes, they have different names. Actually, it's a really good way to think about it. All right, now we're getting into something that people have asked about. And now we're getting into some biological stuff as well. So as I showed you before, double bonds can't rotate. Carbon atoms in a ring can't rotate either. They have a little more. So when you're in a ring, you have a little more flexibility because those are all single bonds, but you can't completely rotate without breaking the ring. So we have what are called cis and trans isomers. Now for double bonds, cis just means that the substituents are on the same side of the double bond. They're either on top or they're on the bottom. Both are on the top, both are on the bottom. We call those cis because they're on this, cis meaning same. So they're on the same side. Trans meaning opposite. They're on opposite sides. So one substituent is above the double bond, the other substituent is below it, and they can't move. They're basically stuck there. So cis would be both your thumbs in one direction, either both up or both down. Trans would be opposite sides. And the same is true with the ring. With the ring, either you're above the ring. So here's, if we want to draw something being above the ring, if you remember, we make the little wedge, that means coming out at you. So if I have the chlorine, this chlorine's coming out above. And if I want to put it behind, I make the little dash like this. That means it's below the ring. So you're either above it or you're below it. So these two, would they be in cis or be in trans?
Trans.
They'd be trans to each other because chlorine 1 is above the ring and chlorine 2 is below it. So they'd be on opposite sides of the ring. So let's look at some examples. So so remember when we're dealing with skeletal structures, this just refers to a methyl group, and so does this. So if I was to draw it, this would just look like that. So those are two methyl group substituents in cyclohexane. So this substituent and this substituent, are they cis or trans?
Trans.
Those are trans, right? Because 1 is above the ring and 2 is below it. What about B?
Cis,
That's cis, right? Are they both above or both below?
above.
Both above, right? They're on the same side. So things that are cis are closer to each other. Things that are trans are further apart. What
'Cause
about C?
one looked like the top and one looked like it was on the bottom. So that's why I thought that one was trans. For B.
Which B?
Yeah.
No, they're both solid. Remember, a solid wedge means coming out, and the hatched line means going behind, means farther away. It's like shorthand for coming out and going back.
So is it because both of them are triangles? That one would be cis.
No, both of them are solid wedges, meaning coming out. So they're both coming out of the screen.
Oh, okay.
So they're both on top of the ring.
Oh,
Yeah. So what about number C here? I haven't got exactly the same substituent. Here I've got an ethyl group on that side, and I've got a propyl group on this side, but they are substituents. So are they in cis or trans?
Trans.
Those are in trans, right? So now when I look at this last one, I just have the skeletal structure. So there's my double bond. And I can see that they have different substituents. One has 1, 2 carbons, and the other one just has 1 carbon. So they're different substituents. Are they on the same side of the double bond or the opposite sides?
Same.
Same side. So cis or trans?
Cis.
This.
That's cis, right? So if we wanted to make that trans, all we would have to do is draw exactly the same thing. 1, 2, 3, and then down. So instead of this one going up, we just have it going down, and then it would be trans. Now there's another form of isomerism in organic compounds. And this are mirror images of each other. That is where the word chiral comes from, basically meaning hand. So your two hands are chiral. Why? Because if you put them facing each other, they're mirror images of each other, right? Your thumbs are on the same side. Your pinky fingers are on the same side. They reflect each other. But one thing you can't do with your hands is put them on top of each other. See, if I put them on top of each other, my thumbs are on opposite sides. There's no way I can put my hands on top of each other with the same side, either the fronts or the backs. I can't put backs together or fronts together where they superimpose on each other. The only way they do that is if they have mirror images. So that happens when you have a carbon that has 4 different atoms or groups of atoms attached to it. So in this instance, we have a carbon here. It has 4 different groups. It has a hydrogen. It has a hydroxyl group. It has a methyl group. It has an ethyl group. 4 different things attached to it in 3 dimensions. So you can have a mirror image of each other, and we call that a stereo isomer, meaning I can't put the 2 of them on top of each other, but they're mirror images of each other. And so that is called a chiral molecule. And an enantiomer is a non-superimposable mirror image molecule. So this molecule and that molecule look exactly the same, but mirror image. So you can't put molecule A on top of molecule B and have all the groups line up. It's impossible. But you can't have mirror images of each other. So we call those enantiomers or stereo isomers. And this carbon we call a chiral center, because that is the spot where that carbon has 4 different groups. And the only way a carbon can have 4 different groups is if they're all singly bonded. So you don't see this in double bonds. You have to have 4 different bonded groups to the carbon. So let's see how that works out. So here we've got, remember, identical molecules you can put on top of each other and everything will line up. Here is a compound called carvone. And a form of it is made in spearmint, and a form of it is in caraway seeds. And the only difference is this group right here. On the carvone, it is coming out of the ring, and in caraway, oh, sorry, it's the other way around. In carvone, it's behind, and in caraway, it's in front. So they're mirror images of each other, but we can't put them on top of each other, because if we put them on top of each other, this one would be behind the rings, and this one would be in front of the rings. Everything else would line up, but that one group would be different. One would be up, the other one would be down. They're mirror images of each other. And not only they mirror images of each other, your body can tell the difference between them, because this tastes like spearmint and this tastes like caraway seeds. It's exactly the same molecule, but they're different shapes. And the receptors in your body can tell the difference because they are sensitive to shapes. Things have to fit into those receptors like a key in a lock. And so this does not fit into the same receptor that this one does. And so your body can tell the difference. We have some other examples as well. So let's figure out how we can determine if something's chiral and where's the chiral center, which carbon is chiral. So we find all the carbons that are tetrahedral, in other words, ones that have 4 bonds. Well, in this molecule, this one is, that one is, this one, and this one. So, and that one. Since there's no double bonds, all the carbons have 4 bonds. So it could be any one of them. So let's look a little bit closer. Now we see if the 4 groups attached to each of those carbons is different. Well, this one's out because it's attached to 3 hydrogens. So those aren't different. That one has 2 hydrogens. That one has 3. That one has 2. So those are all out. So we now have to look and see if there are 4 different groups attached to this carbon or that carbon. So I'll call them A and B. So carbon A and carbon B. So if you have a close look at carbon B has a hydrogen up here, and it's attached to the rest of the molecule on the other side. So those are different, but it has a methyl group here and a methyl group there. Those are the same. So that is not chiral. It has 3 different groups, but it doesn't have 4. So that one's not chiral. So there's only 1 carbon left to have a look at. So let's look at that a little more closely. So if we look at the carbon A, this one, we can see that it has a bromine here. There's a hydrogen here. It has an ethyl group here, and it has a butyl group there. Those are 4 different groups. That is chiral. And we typically just put an asterisk next to 1, 2. That's probably enough for an asterisk, right? This carbon is chiral. So that is a chiral molecule. And one way we can tell whether or not a molecule is chiral, we can tell this in the lab without even like taking it apart or anything. Anyone know what polarized light is?
I just know it lets you, when you have polarized sunglasses, you can see the coral underneath the water surface, but I don't know why.
Okay. What your sunglasses do if they're polarized, what a polarizer does is if typically like light coming from a natural source is in all different directions. You've got waves that look, they're coming in that direction. You get waves coming in this direction. You get waves coming in this direction, coming in all different directions. So what a polarizer will do is it will basically block out all the light except one going in one particular direction. So what the polarizer will do with all those lights, all those different waves, is turn them all into waves going in the same direction. So they're all going in one direction. So what we do is we take polarized light and we shine it on these chiral compounds. And what the chiral compound will do is it will bend the light in one direction or another. One orientation will bend it clockwise. Another orientation of these molecules around the carbon will bend it counterclockwise. And that's how we can tell the difference between the different orientations. And so we call them S and R is one way we call them. One for R, for it rotates it clockwise, and the other S, it rotates it counterclockwise, or sinister, or left-handed, because we all know left-handed people are sinister. So we call one compound S and the other one R. We also call one L and the other one D. This one actually comes from the rotation of the light. This one rotates it counterclockwise and this one clockwise. So they're either called L or D or S and R, basically the same thing. They're just different combinations of how those substituents are arranged around the carbon. And it has real biological importance. So let's have a look at these and see if we can find any chiral centers. So let's look at this molecule first. So we've got 1, 2, 3, 4, 5 carbons. Any of them attached to 4 different groups. Basically, there's really only one candidate, right? What's the one candidate we have for being chiral?
Carbon 3.
Number 3, exactly. It can't be this one. It can't be 1. And it can't be 5 because those are just CH3. And it can't be 2 and it can't be 4 because those have 2 hydrogens attached to them. So really the only one it can possibly be is this one. So let's have a look at it. It has a hydroxyl group on one side. It has a hydrogen on the other side, and it has that on one side and that on the other side. So is that chiral?
Is it yes?
Okay, why do you think it's chiral? Are these two groups the same?
Actually, no.
That's right, those two groups are the same, right? So since they're the same, it only has 3 different things attached: a hydrogen, a hydroxyl group, and a propyl group. So those 2 are the same. So that's not chiral.
Because it doesn't have that perfect symmetry. I don't know how to describe that, but
Yeah, and it's symmetrical. That's right. It's symmetric. So this is the same as this. So that basically tells you right away that that can't be chiral, because if it's completely symmetrical, it's the same one direction and the other. So yeah, it's a really good point. Symmetry is a good way of determining whether something can be chiral. If it's completely symmetric, then it can't be chiral because you can just spin it and it's the same each time you spin it. If you spin it 180 degrees and it's different, then it's not symmetrical. So let's look at B. So here we've got 1, 2, 3, 4, 5 carbons. So which ones could be chiral?
So 1 and 3.
Yeah, 1 and 3, right? 2 can't be because 2 has 2 hydrogens attached to it. So that can't be. And 5 has a hydrogen, carbon. It has a double bond. So right there, it only has 3 groups attached to it. So that can't be chiral. So this one's out, that one's out, that one's out. So really we're left with the carbon attached to the chlorine and the carbon attached to the hydroxyl. So are either of those chiral?
I'm wondering if it's no, only because one is a chlorine and one is a hydroxide. Like, does it have to be the same on both ends?
No, 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 no. The only thing we need to think about for a chiral center, does it have 4 different groups attached to it? That's all. Doesn't matter what they are they different? So that could be chlorine, it could be iodine, it could be a methyl group, it could be anything, doesn't matter. As long as that particular carbon right there and that one right there has 4 different things attached to it. If that's the case, then it's chiral.
So yes, because of the double bond.
Yes, they're both chiral. Excellent. Right, because this carbon right here is attached to chlorine, hydrogen, and it has a single bonded carbon on one side and a double bonded carbon on the other. So that's chiral. Those are 4 different things. And the same thing is true with this one. It has a hydrogen, it has a hydroxyl group, a single bonded carbon on one side and a double bonded carbon on the other. So that is chiral. Excellent. Those are both chiral. What about C here?
Sorry, question. So the asterisk, you put an asterisk next to
Right. So we put the asterisk right where the carbon is. Yeah.
on the inside of the structure.
On the inside. Mhm. So we've got cyclohexane. We have bromocyclohexane in C. So it's got 6 different carbons. And that one's going to be automatically called 1 because it has a substituent on it. So basically, that's the only carbon that could be chiral, right? Everybody else has 2 hydrogens attached to it. So they can't be chiral. So is this carbon chiral, the one that's attached to a bromine?
Yes.
No.
Yeah, no, because this going that way and that way are equivalent. So it's got attached to a bromine, it's attached to a hydrogen, and then the other 2 sides of it are attached to exactly the same thing. So going in this direction and going in this direction, you get exactly the same thing. So it's not chiral. Okay.
I'm just wondering, so I guess kind of another way to explain it is if you can fold it in half, like a sandwich almost, like if it has the same components.
If it is, yeah, if it had two,
Because for that one, you said it's just like A, where if you split it in half, it's that, I guess the symmetry of it is that it's going to be the same on both sides, but for it to be chiral, it has to be an exact replica or like not an exact replica, but the other half of the structure has to be the same. I don't know if I'm explaining that correctly.
yeah, basically you need, you have to think about that one for a minute. Yeah, there's lots of different ways to think about this. I find it a little confusing myself, actually. But yeah, basically, can you get a different, can you put it together in a way that, well, actually, let me think about that one a little bit more. I would have to give that one a little more thought. But yeah, I just wanted to bring this up because someone mentioned this earlier. Chirality is super important. In fact, so important. The winners of the Nobel Prize in Chemistry won it for coming up with a way of making chiral molecules. So, and actually one of them was a postdoc at the same place I was a postdoc. So, get to celebrate him a little bit. But what the breakthrough was that typically in doing making catalysts, metals are used a lot because you can absorb things on metal and you can push reactions forward that way. But metals aren't chiral. And so you would make both enantiomers, you'd make both stereo images of the molecule. And one of them is useful and the other one is useless. And it's really hard to separate them because chemically, I mean, they're identical, right? For all intents and purposes. So trying to separate them from each other is really hard. So what the idea they came up with was using a small organic compound as the catalytic center, because this is chiral. So if you start with a small chiral molecule, the molecule you make is going to be chiral too. And so that they came up with this idea about 20 years ago, and now it's like everybody uses it in chemistry. So instead of making like large enzymes, which also make enzymes make chiral products as well because they're huge and they have a distinct shape inside them. The breakthrough they made was if you start with a very small chiral molecule, you can basically force the chirality on the rest of the molecule as well. It's much, 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 much simpler to do. In fact, these are like really simple chemicals that most people have on the shelf of their lab. So big, big breakthrough there. Okay. So give any questions before we get to the worksheet? Oh, what I will do is I will include it in the chat just in case you don't have it. And then give everyone like 5 minutes to take a break. I know I need a little break.
Is there a simple way to think of chirality? Because the examples you gave, it was just kind of confusing. It seemed like chirality had to do with something being not symmetrical.
Right. Yeah, I think I'll try and come up with there's more than one way to think about it, but I need to come up with one sort of overarching way to think about it. So yeah, let me work on that a little bit. Because yeah, it's such an important concept. I want people to be able to get it. Yeah, and since there is more than one way to think about it, probably one overarching way to sort of identify chiral centers would be not a bad idea. All right, is everybody back? Oh, let me switch this around. There we go. So the way I like to do these is basically find the root. What's the sort of the root structure of each of these compounds? And that's going to be at the end. So for instance, pentene, how many carbons is that? Pen.
5.
5, right. So it means we're going to have 5 carbons in a row. So we just go 1, 2, 3, 4, 5. And then what's this number? What's the number in front of it? What's that 2 refer to?
Double bonded on the second carbon.
Right. So there. So that means that is 1, that's 2, 3, 4, 5. And then I look for substituents. 2-methyl. What does that mean?
There's a methyl group in the second carbon.
Right. And what's a methyl group?
It has a CH3.
CH3, right. And then you're done. Basically, at this point, you just have to add the hydrogens. So 1 would have 3. 2 wouldn't have any because it already has 1, 2, 3, 4 bonds. Carbon 3 has 3 bonds, so it would get 1. And carbon 4 gets 2 because it only has 2 bonds, and then 3 at the end. So that would be your sort of basic Lewis structure. And then as far as the skeletal structure goes, we do the same thing. So pentene has 5. So we go 1, 2, 3, 4, 5. And it has it's a double bond at 2. And it has a methyl group at 2. Then you're done.
Does it matter where the double bond is drawn? Like above or below? that
No,
line?
no. As long as it's between carbon 2 and 3, you can put it there or you can put it there. It doesn't matter. Yeah, that part doesn't matter. All right, what about the cyclohexene? Who can,
Where's all the other ones? No more? Okay.
so how many carbons is that? Hexene,
I need to drink it all.
6.
6, right. So I have 6 carbons, but they're not in a line, are they?
It's cyclo, so it's in that circle where
ring.
the
Right, so we got to go 1, 2, 3, 4, 5, 6. And then everyone's got 1 single bond, but it's in hexene. So what does that mean?
means a double bond.
Means one of them's got a double bond. Does it matter where I put it?
No.
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 Because wherever I put it, that automatically becomes carbon 1. So that is carbon 1. And since there are no substituents, we don't need to name it. So that's it. And then we just would fill in hydrogens. 1 there, 1 there, and then everybody else gets 2. And that's it. And as far as drawing cyclohexene in the skeletal, that's as simple as it gets, because you just make 1, 2, 3, 4, 5, 6, and then I just put a line. It doesn't matter where it is, because basically I can just spin that around and it's all the same compound. So it doesn't matter where you put the double bond.
This
Can
looks
you draw the
confusing.
hydrogens for that one? For like the additional hydrogens? Do you do one on the inside and on the outside of the structure?
Well, for the
Or-
skeletal, you don't put any hydrogens on it because we don't include them.
This.
Okay.
But for
So
the
you don't have
Lewis
to draw them at
structure,
all. Yeah, that's what I mean for the Lewis structure.
this gets 1, that gets 1, because they already have 4. They already have 3 bonds, so they only have room for 1 more. And then everybody else gets 2. So 1, 2.
Oh, that's what I mean. So you can,
two.
you do draw it on the inside.
1, 2. You can, or you can draw them there. Either
Okay.
way. Just as long as they have the right number.
Okay, thank you.
Yeah, so 1 and 2 both get 1 hydrogen and everybody else gets 2. And then, all right, so who wants to name some of these? What did we get as a name for the first one?
Netherlands. It's okay.
Is it 2-methylbutene?
Turn up.
I know you gotta search this out.
So you're right about so it is 2-methyl.
I mean,
It is
those.
butene, but you're missing a piece of information.
Because I thought that because it was
Is it
double
1
bonded on
butene?
the first one, you didn't need to write, 1-butene.
You have to do that because it's got 4 carbons, so you don't know whether the double bond's on 1 or 2.
Oh,
Yeah,
I thought it just, you have it like this. You don't really have to write 1-butene.
no, because it could be that.
Oh, so it's only if it's,
That's
what was it?
2-butene.
I think you said in the lecture or something that if it was 3 carbon
It
groups,
was 3 carbons, then yeah, it
Then
doesn't
you
matter.
don't.
But
but in this case, yes, you do have to write.
if it's
the-
4, then you have to say, because
Oh,
if it's
okay.
3, then it's either there or it's there. And in either one, it's like either that's carbon 1 or that's carbon 1. It doesn't matter. But when you have 4 carbons, the double bond's either going to be between 1 and 2 or 2 and 3. So you have to say whether it's on carbon 1 or carbon 2. This one is on carbon 1, so you have to say that. So 2-methyl-1-butene. What about the second one? Who came up with a name for the second one?
Was it 5-methyl-2-heptene?
Excellent. Yeah, there's 7 carbons. 1, 2, 3, 4, 5, 6, 7. And there's a double bond in it, so that's heptene. And you have to say which carbon it is, number 2. So that's 2-heptene. And then you have to tell where there are any substituents, and there's 1 there. 5-methyl. Excellent job. What about number 3?
Sorry, I was gonna ask you about that one. I read it different. So instead of me counting from left to right, I counted from right to left.
Yeah, the double bond gets priority.
Oh, okay.
Yeah,
Because
so you have
I
to
thought you
give
said,
you have to give the carbon with the double bond the smallest number possible.
oh, okay, because I thought you started with the substituents, because that's what you did in the example.
That's what you do when you have alkanes. Remember I said that the only difference between alkanes and alkenes is that with alkenes, you have to give the smallest number to the double bonded carbon. That gets priority.
Oh, okay.
Yeah, and then everyone else takes their numbering from that. But with an alkane, there are no double bonds. So yeah, in that instance, you want to give the substituents the smallest number possible. That's the
Oh.
difference. Yeah, good point. What about number 3 there? A lot going on with that one. What's the longest stretch of carbons containing the double bond we can make?
It's a hexene.
So we got 1, 2, 3, 4, 5, 6, right? So
So
it's a hexene.
I think this one, is this the one where it's like, it's a dimethyl because there's the methyl on both sides?
I see more than 2 methyls.
Yeah, but with the root, I guess, is it like a 2,4 dimethyl because of the methyls being on both sides?
There's more
I
than
think you have to list
there's
two
more
twice.
than there's more than 2 methyl groups though. There's 3.
Is it
There's
2
one there,
dimethyl
one there,
and then
there's one there.
2-dimethyl, 4-methyl,
No.
3?
I think you list the two times.
There's 3 methyl groups, so you need to account for all 3.
Oh, so you do 2 times. So 2, 2.
Yep,
So 2, 2, 4 methyl.
that's right. 1, 2, 3, 4. Yep. 2, 2, 4, and then what do you say?
So 2, 2, 4 dash methyl dash 3 dash hexene.
No, but methyl says
Trimethyl.
Or trimethyl.
trimethyl, exactly.
Oh, I
Because
see.
there's
Okay.
3 of them. Yeah,
Okay, I just put the wrong, I put di instead of tri. Okay, I get it.
and you're still missing a piece of important piece of information.
The 3, right?
The 3, right?
That's
Before
where the double
hexene.
bond is for the
So
hexene.
2,2,4 trimethyl 3-hexene. That's a mouthful.
Is there another way you can write it? Like, I don't know, like
So two,
dimethyl,
two,
you know,
and then
for the 2
four.
dimethyl, and then I don't know, maybe you can put like
Yeah,
1,
there's
2, 3,
One,
you
two,
can do it
four,
that way, but that's not right. I
4,
mean, you have to account for all 3
three,
methyl groups.
four. No. I mean, maybe you can
And
write something
3
like,
hexene is like
am I getting?
at a 3. It starts at the double bond, so 3. Hexene is like there's
Hex is 6.
six.
Yeah, there's
carbons.
6. There's 6 across. That's the longest stretch of carbons we can make that contains the double bond. So that makes for the hex part. That's 6. In either direction we go, it's going to be the 3rd carbon, either direction. So the smallest numbers we can make for the 3 methyl groups are 2 and 4. So 2, 2, 4. And there's 3 methyl groups. And this is where the double bond is. So that gives us all the information we need.
Because initially I thought maybe you could write like 2 dimethyl because carbon 2, there's 2. And then later maybe you could, I don't know. I didn't realize there was.
No, you have to make the name as small as possible.
Oh,
So you wouldn't call it 2-methyl, 2-methyl, 4-methyl. You just give the positions of where they all are.
okay.
2, 2, and 4. And there's 3 of them.
Okay.
Yeah, okay. Let's look at. Ooh, phenyloctane. So what's the root here? What's the root compound?
Octane.
Octane, right. So how many carbons is that?
8.
8, right. So 1, 2, 3, 4, 5, 6, 7, 8. And it's an octane. So are there any double bonds?
No double bonds.
No
No.
double bonds. What's this? What's that 3-phenyl? What does that refer to? What's a phenyl group? That's a new one for us. That's a new one for this chapter. What's a phenyl group?
So that's from phenol. So that's one of the rings.
Right, it comes from the ring structure. That is benzene, but when it's attached to something, when we covalently link that to another carbon, we call this a phenyl group. Because phen is the original name of the group. And then so phenol, which is in another question, phenol, all means it has a hydroxyl group on it. So that's what phenol is. Phenyl is when this group is attached to the carbon. So which carbon is it attached to?
3.
3, right. So 1, 2, 3. So we just attach. That's a pretty bad one. We just attach a phenyl group there. So you can do it that way, or you can make the circle in the middle. So as far as the Lewis structure would go, just 8 in a row. And then off the third one, we have 1, 2, 3, 4, 5, 6. And then just fill in the hydrogens. Okay. All right. Number 4. Had a lot of people with questions about number 4. So first, before we write the chemical equation, so the chemical equation would just be, what are the formulas for everything? And people had a lot of trouble figuring out what the formulas were. So let's actually write the structures first, and then should be able to figure out what the formulas are. So what's cyclopentene? What is that? Pen, how many carbons is that?
5.
5. And so cyclo, what does that
5.
mean?
It's in a ring.
It's in a ring, right? So that's 1, 2, 3, 4, 5. It's just a little house. That's
And
how
one is
everything-
double bonded.
And one of them's double bonded, right? So that's C5. And how many hydrogens would that be? So
Is it
I've got
11?
1, 2, 3, 4, 5 carbons. How many carbons are going to be, how many hydrogens are going to be attached to numbers 3, 4, and 5? How many bonds is carbon 3, 4, and 5 making?
Is it 2 hydrogen?
2 at each one, right? Because each one of these is making 2 bonds. One going in that direction, one going in that direction. So this carbon is making 2 bonds. So it would have room for 2 hydrogens. 1, 2. Same with carbons 3 and 5. So 2 can go here, 2 can go there, 2 can go there. What about carbons 1 and 2? How many bonds are they making?
3.
They're making 3, right? There's 1 here, but there's 2 there. So they're each making 3 bonds. So how many hydrogens can they bond to?
Just 1.
Just 1, right? 1 there, 1 there. So 2, 4, 6, 7, 8. So that's the formula for cyclopentene. So my chemical equation is C5H8 plus water with sulfuric acid makes cyclopentanol. So even if we don't know what cyclopentanol is, what can we tell about cyclopentene plus water?
One will have a OH. Because
So-
the O.
Right, so so that's carbon
And then
1,
it's-
2, 3, 4, 5.
And it will also be in a ring shape too.
So what's going to happen to carbons 1 and 2?
Will one just have a OH and one just have a H?
Right, one has a hydroxyl group,
And in this case, it
and
doesn't
the other
matter
one
which
has
one,
a hydrogen attached. Right.
because you said in some cases it does matter where you put it.
It will matter if these had a different, if 1 and 2 were attached to different things, it would matter. But 1 and 2 are identical. So they're equivalent to each other. They're each attached to the same thing. So it won't matter which one of them will get the hydrogen, one of them will get the hydroxyl group. And it's 50-50 for this one. That's where the all comes from. All means it's an alcohol, and it's an alcohol, we'll learn this next chapter, because it has a hydroxyl group attached to it. So what I'm going to get is the double bond goes away, and one of them gets a hydroxyl. The other one gets a hydrogen, but we don't draw hydrogens on skeletal groups. That's what the skeleton looks like. That is cyclo, because it's in a ring, pentan, because it's 5, and all, because it's an alcohol now. So what's the formula for cyclopentanol? C5. How many hydrogens?
9.
So 2, 2, 2, 2, We're missing one. Remember, there's another one there.
Oh,
Because
okay,
this-
10.
Right, 10. H10O. It's also written sometimes C5H9OH because we chemists like to put like the functional group at the end. So sometimes we'll do it like that just to let you know it's an alcohol. So either way is fine. So my final formula is C5H8 plus water gives you, and you should be able to figure this out just from the formula, right? Gives you C5H10O. Because remember, we're just adding 2 hydrogens and an oxygen. All right. Gotta hurry up here. All right, anyone have, the only one will have difficulty, I think, on this one is C, because I didn't tell you what phenol is. But as I mentioned, phenol is just benzene with a hydroxyl group on it. So this becomes position 1. So where would the ethyl groups go? So it's diethyl, so it has 2 ethyl groups. What positions would they go?
2 and 4
So where's, so 2 would be where?
to the left.
Or on the right, either way, right? It doesn't really matter.
Yeah.
So
Right.
let's put it there, 3, 4. So ethyl is just 1, 2, and then ethyl group here, 1, 2. So what's another name I could give this? I'd still call it phenol. I'd still call it diethyl phenol, but what's the other name I could give it? What's the relationship between these 2 ethyl groups? As
Meta.
substituents. What is it?
Meta.
Meta, exactly. So that would just be meta diethylphenol. Excellent. Great job. All right,
So do you just
number,
write an M in front or you write?
yeah, just an M. Mhm.
Just M, okay.
All right, let's do one of these. Anyone get this far? Did anyone get to
No.
number 6? All right.
No.
All right, let's so now we get to use Markovnikov's rule because we're going to have unequal substituents on either side. So propene, how many carbons is that?
3.
3, right. So I go 1, 2, 3. And it's a propene. So what does that mean?
Double bond on the first.
Yeah, means I got a double bond. It doesn't matter where I put it. If I put it there, that becomes carbon 1. And if I put it on the last carbon, that becomes carbon number 1. So 2-methyl. So that means I've got a methyl group here. And then I just fill in the rest. So there's no hydrogen there. What am I doing? That's already got 4 bonds. So this has 1, 2 hydrogens. And that has 3. So what happens? Which carbon? So I got carbon 1, got carbon 1 and carbon 2. So that's the double bond that's going to get broken. And when it gets broken, I'm adding water across that double bond. So one of those carbons is going to get the hydrogen, and the other one is going to get the hydroxyl group. So who's going to get the hydrogen? Carbon 1 or carbon 2? Remember what Markovnikov's rule was? Do you remember what it
Carbon-
was?
3. You said more hydrogens get more hydrogens.
Right. So who gets the hydrogen? Carbon 1 or carbon 2?
Carbon
Carbon.
1.
Carbon 1, right. Carbon 1 is only attached to hydrogens. So it's going to get another one. So when this bond breaks, carbon 1 is just going to get another hydrogen right here.
Not carbon 2, because carbon 2 has 3 hydrogens, right? So wouldn't it? get
Carbon 2
more?
has no hydrogens.
Oh, sorry, I was looking at the CH3. That's why I was.
Yeah,
thinking
carbon
it had
2
to
has
be-
is attached to a carbon there, and a carbon there, and a carbon there, and it actually has 1 hydrogen. So for its
Oh,
total.
okay.
Oh,
I was looking at the.
oh, wait a minute. No, it doesn't have any because it had a double bond there. What am I saying?
Oh,
It
okay.
had a
Yeah, I
double
was looking
bond, so it
at.
didn't have any.
I was looking at CH3, so that's why I thought it was.
So that's
carbon.
where the hydroxyl group goes. So this is your new product. So what would we call that? So it's got 3 carbons. So what would be the root?
Propane.
Propane.
Propane, right? So we go pro, pan, all, because it's now an alcohol. So we say propanol. And we have to say where the hydroxyl group is. It's at position 2. And then, does it have any substituents?
Yes.
It does. What's the substituent?
So is it 2-methyl?
Methyl.
2-methyl, exactly. Excellent. 2-methyl, 2-propanol. Great job. So you'll find when you do B and C, you should get the same product. At least I did, unless I screwed it up. So let's look at the skeletal structures for these. So propene is just 1, 2, 3 with a double bond there, and 2-methyl, that's it. So that is it. And the product would just be 1, 2, 3. There's our methyl, and then the hydroxyl there. So yeah, you see that the much easier to draw the stick figures, or at least it's a lot faster. So let's quickly.
Wait, sorry, I got confused. So
Oh.
you drew 2 different structures just now.
Yeah, this was the reactant, 2-methyl propene.
Okay,
1, 2, 3, 3 carbons.
okay.
Double bond goes at positions 1 and 2,
Uh-huh.
and it's got a methyl group at 2, so it's a straight line.
Yes, okay.
And then the product, you get rid of this,
Oh, I see. Okay, got it.
break the double bond, and you put a hydroxyl group there. So that's it. All right, let's look at now carboxyl group. A carboxyl group is this. That's a carboxyl. I tried to draw it. I don't know if I did a very good job. So I have 4 carbons, 8 hydrogens, and 2 oxygens. And you can see that this has 2 oxygens already. So basically, I am stuck with what I'm left over is C3H7. That's what I have to play with. So go 1, 2, 3, and think how many places you can put that. Basically, there's 2 places you can put it, right? It either goes there or it goes there. So there's really only 2 structural isomers you can draw. I will let you draw them. Getting real quiet now. All right, so number 8, I'll do a couple of them with, I guess nobody got this far. So, so when we look at these, they're either going to be exactly the same molecule, they're going to be different forms of the same molecule, or they'll be mirror images of each other. They'll be stereoisomers.
Is the first one stereo?
Yeah, this is a stereo. These 2 are stereoisomers. Yeah, the only difference, yeah, this one's, those are mirror images.
Forward.
So that one's coming forward and this one's going back. Yeah, so those are mirror images. What about these 2?
Well, they're neither structural or stereo nor identical, so it must be structural.
Nope, these are stereoisomers too, because the only difference is, I'm sorry, this group here. So they're non-superimposable.
Oh, right.
You can't
Okay.
superimpose them on top of each other. So the only difference is that methyl group is pointing up, this methyl group is pointing back. So you can't lay them on top of each other. But what about these 2?
Is it still stereo because they're just
Actually, they're not.
They also look possibly
Identical.
structural.
Nope.
Would it be identical? It's just that one's
They're identical,
one's
right?
above
Because
and then one's below. But
if
if
I
you put them on
flip,
top of
if I
each other, it's
flip
the
that
same.
around, it would be that. If they were mirror images of each other, both of them would be pointing in the same direction, like these 2. Those 2 are mirror images of each other. So I can't superimpose them on top of each other. But these 2 I can. If I flip this around, it would look exactly like that. So I could lay them on top of each other. These 2, I can't lay them on top of each other.
So then
Because if I flip this one around, then the hydroxyl will be pointing backwards rather than forwards. With this one, so if I flip this around, oops, if I flip this around, it would look like this. It would be the hash marks. It would be pointing back. So those wouldn't superimpose on each other. But if I flip this one around, it looks exactly like that. I can sit those on top of each other. All right, we'll do some more work on these. We just got introduced to this tonight, so it'll take some time.